Welcome back, class. In this video, we're going to go over more derivative rules, or derivative shortcuts if you prefer, that will make even more functions easy for us to take the derivative of. But to start with, I want to finally answer the question, what makes e so special? And I want to remind you, e is this weird transcendental 2.7181 blah 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 sort of number. And it is the base of what we called the natural log. And we talked about how you could really take a logarithm with any base. Scientists, again, tend to like log base 10 of x. Computer people tend to like log base 2 of x. And as I mentioned, mathematicians tend to like the log base e of x, or as we call it, the natural log. Okay. So in this video, we finally get to answer the question, or at least partially answer the question, what is it that's so special about this number, and what is it that's so special about this logarithm? And the thing that's special about both of these concerns derivatives. Namely, we have two new formulas. So the first new formula is what happens if you take the derivative of e to the x, and the second new formula is what happens if you take the derivative of the natural log of x. Now, the somewhat remarkable thing that happens when you take the derivative of e to the x is that you in fact get e to the x again. Okay. E to the x is its own derivative. This is very different than something like when we took the derivative of x squared, we got 2x, and so on. This function is its own derivative. Now, if you compare that to something like the derivative of 10 to the x, well, this works out to be 2.305 ... times 10 to the x. This formula is not nearly as pretty. And indeed, for the rest of this course, I will never require you to know this formula. But I will require you to know this formula. What about the derivative of log of x? Well, the derivative of natural log of x happens to be 1 over x. Surprisingly simple. No e's, no constants, no weird things. The derivative of natural log of x is just 1 over x. Again, if you choose to take the derivative of other logs, like the log base 10 that scientists tend to like, you get something uglier. But just like this derivative, I'm not going to ask you to know this derivative again, but I will ask you to know this derivative. So these are two more classic functions that we know how to take the derivatives of. E to the x and the natural log of x. But my hope is that from this you can see that e is this number with the special property that if you take e to the x and take its derivative, you get e to the x back. And natural log of x is the special log with the property that if you take its derivative, you get 1 over x. And these two facts are related, and this is why mathematicians tend to like working with e. Here's an example of a function that, courtesy of our rules that I just told you, plus our rules from today, we can now take the derivative of. Remember, we're going to view 3 e to the x. That's 3 times e to the x. Similarly, this is 7 times the natural log of x. And so when I go to take this derivative, I'll get 3 times the derivative of e to the x. But remember, the derivative of e to the x is e to the x minus 7 times the derivative of natural log of x, but that's 1 over x. Okay. And then we've got to look at this e squared. And so, what is the derivative of e squared? Well, there are two answers that might pop to your mind. Namely, if I take the derivative of e squared using the power rule, I would get 2e. But if I took the derivative of e squared using this rule, I would seem to get e squared. So which is it? Which of these is the derivative of e squared? It can only be one of these. Well, I lied, actually. It's neither of these. These are both wrong. Now, it's very understandable to fall for this and think one of these would make sense. But what's actually happening here is that e squared is a constant. Again, how do I know this? There's no x's here. So when I talk about what happens to the value of this thing in the brackets when I change x, well, nothing happens to e squared. It stays e squared. And so e squared is a constant. And remember, the derivative of a constant by itself is always 0. And so we get 3e to the x minus 7 over x. And that is the value of this derivative. And of course, we've amassed all of these skills over this course of things we can do with derivatives. So we can again do those sorts of problems now with functions that have an e to the x or a natural log of x in them. So we can, for example, find equations of tangent lines. So this question, for example, we're going to start by finding the derivative here, which I'm going to use the same rules as before. So this is going to be 5 times the derivative of a natural log of x is 1 over x, minus 3 times, and the derivative of x is 1, plus, and then the derivative of 7, but the derivative of 7 is 0. And so the derivative of our function here, f prime, is 5 over x minus 3. Now I need to use this derivative in order to find the slope of the tangent line that I'm looking for. And so remember, that slope is going to be f prime of the input, so that input is 1. And so this is going to be 5 over 1 minus 3. In other words, my slope here is 2. So I've got my slope, I've got my point. Oh wait, I don't actually have my point. In a lot of my previous examples of finding equations of tangent lines, I've given you something like this, where in the question, I gave you the point. Here I did not actually do that, I only gave you the x-coordinate of the point. So I need to make sure I also find the y-coordinate. And remember, all the points on the graph of a function are input-output pairs. So the second point here must be the output of f of x at 1. Note, it's the output of f of x, not the output of f prime of x. Okay, the natural log of 1 is 0, you'll recall from earlier. So minus 3 plus 7, that'll be plus 4. And so our point here will be 1, 4. And so at this point, all of the calculus is done. We now just have to find the equation of a line which has slope 2 and passes through the point 1, 4. And so the equation of the line looks like y equals 2x plus b. We need to figure out what b is. Okay. Well, to do that, I'm going to plug in 1, 4. And so I'm going to find that b is 2. And so the equation of my tangent line works out to be y equals 2x plus 2. I'm going to wrap this video up here and keep it a little bit short. And in the next video, we're going to introduce the product rule, which is really going to break open the sorts of functions that we can take derivatives of. But that's all for now. I'll see you next time.